collaboration with Institute of Engineers India, that is II Local Students Chapter. I am Vashta from the Department of Electrical and Electronics Engineering, Vastreddy Venkatadri Institute of Technology. Once again, welcome all the participants to 10th session of this national level online FTP. Today's our chief guest and speaker is Dr. K. Giribabu sir. Warm welcome Giribabu sir. Thank you for accepting our request to be in the part of this FTP. Before hand over this session to the Giribabu sir, let me introduce today's speaker. Dr. K. Giribabu sir is currently working as a professor in ECE and Dean of Academics at Vastreddy Venkatadri Institute of Technology, Nambur. He completed his BTech in the stream of Electronics and Communication Engineering, Guntur, ME in Electronic Instrumentation, Department of Electronics and Communication Engineering from Andhra University, Visakhapatnam, and PhD in Image Processing in Electronics and Communication Engineering in JNTU, Hyderabad. He is continuing his research through publications in 47 international journals in SCE SCIE, Scopus, 15 international conferences. He has completed 2 research projects and 7 research projects are ongoing with the overall grant amount of nearly 1 crore. He received Best Researcher Award from JNTU Kakinada and Best Teacher Award in Electronics and Communication Engineering from ISTE Andhra Pradesh. He got ratified as professor by JNTU Kakinada. He has 24 years of teaching experience. He is a member in Executive Committee IEEE, Fellow in the Institution of Engineers, Life Member in ISTE, and Life Member in IAENG. It is my privilege to welcome such a noble personality, our chief guest, Dr. K. Giribabu sir, to start the session.
Good afternoon, all the participants. Sir, Baksing, sir, share in
Yes, sir. Share in, sir. At full screen mode.
పెడుతున్నా.
Yes, sir.
So, good
Yes, sir.
afternoon, one and all. Okay, I welcome all the participants of this faculty development program on electric vehicles, technological advancements, and trends. And this is the 10th session. So, from the last 4 days, we are discussing about electric vehicles. Okay, so electric driving systems, normally we all know that they doesn't require any fuel to operate. So as such, they have neither a petrol tank nor a combustion engine, but rather an electric engine powered by a battery. So electric vehicles, normally they are also termed as battery electric vehicles. So almost nowadays they can present electric vehicles. They can cover a distance from 100 to several hundred kilometers. Okay. Now coming to autonomous vehicles. So autonomous vehicles are self-driving vehicles. So here we'll discuss about cars. Okay, autonomous cars or self-driving cars. Generally, they use electricity to run. That means all autonomous vehicles are electric vehicles. Okay. So the autonomous vehicles are like this. They are connected and fitted with an embedded driving or a communication system and a high-tech set of sensors. So the sensors normally we'll discuss about the sensors also like cameras, lidars, radars, like those. So all these enable them to operate safely without requiring a driver. Okay. Now we'll discuss about how the self-driving cars work. So the first self-driving car was invented in 1989. Okay. And they have used a neural network known as Alvin. Okay. The abbreviation is automatic land vehicle in neural network. They have used this neural network for the first self-driving or autonomous car. Okay. So here the neural networks, they are used to detect lines. 1 minute. So they are used to detect lines. Okay, segment the images. Okay, like this. So segment the images means we have to segment the environment. Okay, navigate and drive. Okay, so this system, it works well, but the problem during 1989 is the computational power is very less. At that time, just we are using only Pentium processors. So we have very slow processing powers and also insufficient data. Okay, but nowadays we have very high performance graphic cards, NVIDIA graphics. Okay, even in laptops we have RTX 3080 Ti. Okay, that means 12 GB GPU. So the with high power graphic cards, okay, and huge, which can process a huge amounts of data, self-driving is more powerful than ever. Okay, so here basically the self-driving cars, okay, now at present they are autonomous decision making systems. Okay, now the systems are manufactured in such a way that they can process streams of data from different sensors such as cameras, LiDAR, radar, GPS, or some sensors like inertia sensors. Okay, so for this self-driving cars, we will use deep learning. Why we have to use deep learning? Means deep learning is one of the main technologies that enabled self-driving. Okay, so deep learning is in such a way that it is a versatile tool that can solve almost any problem. Okay, and in this session specifically, we'll focus on deep learning algorithms in self-driving cars. That means we will concentrate on convolution neural networks. Okay, we'll concentrate on convolution neural networks because we know that uh, Tesla and NVIDIA and also Google, okay, they are participating in autonomous cars. Okay, they are producing, some are doing manufacturing. Okay, so they are using convolution neural network systems, okay, in autonomous cars. Okay, normally Tesla, they are using HydroNet. Okay, NVIDIA, they are using self-driving car. Google ShafferNet. Okay, so in this session, okay, along with convolution, first we'll discuss about convolution neural networks, and then we will discuss about the data that we require for self-driving cars. Okay, and then we'll discuss about how we can process that data using convolution neural networks. And lastly, we'll discuss about the CNN, the convolution neural networks model used by Tesla and also NVIDIA. So why convolution neural networks? Okay, why deep learning? Okay, so we all know that neural networks are very good at image recognition. Okay, but why we are going to deep learning instead of machine learning means, just let us take a 64 by 64 by 3 image. So if you consider 64 into 64 into 3, That means we'll have 12,288 input parameters. So to process these images, we can use neural networks. Okay? Because it is a very small image. The size of the image is very small, 64 by 64 by 3. But here we have, if you consider an image having a size of 1000 by 1000 by 3, that means almost we'll have a 3 million input parameters. We'll have 3 million input parameters to process. That means this much very high number of input parameters, they will take a lots of time to process, and it requires very high computational power. As nowadays we are having high power graphic cards, okay, so we can easily process high images, okay, which consume larger data. Okay, so now the problem space is like this. So we all know that neural networks are good at image recognition. Okay, so the problem space for convolution neural networks are like this. They are very good at only image recognition. They are very good at image classification. The basic application of convolution neural networks is image classification. So here, if you take different images, so here I have considered a bird image, sunset, dog, cat. Okay, we have a set of data, input data set. Okay, if you give the data set and train the convolution neural network, okay, the output is such that we can perfectly classify, okay, a, a bird, sunset, dog, cat, like this. We can perfectly classify images. Okay, so the basic building blocks of convolution neural networks are like this. So first we will have convolution layers. Okay, we'll have convolution layers and then rectified linear units, ReLU, which are activation units. Okay, we'll have along with convolution layers, we'll have rectified linear units. Okay, after convolution and rectified linear units, we'll have a pooling layer. Okay, after convolution, ReLU and pooling, we'll have another set of convolution, ReLU, pooling. Okay, if we have more than 3 layers, more than 3 or 3 layers, okay, we can call them as deep convolution neural networks. Okay, more than 3 layers. So first we'll have the layers are like this. First we'll have convolution, ReLU, layers of convolution, ReLU and pooling. Okay, using these convolution, ReLU, pooling, we are making our network to learn about the features. Okay, so our network, okay, will learn about the features of the input data. Okay, and then using the second set, okay, second, this is the classification part. This is feature learning part, and this is the classification part. Okay, here in classification part, we'll have a fully connected neural network. Fully connected neural network, and using this fully connected neural network along with basically normally we'll use a softmax activation function. Okay, using fully connected neural network and an activation function like softmax, okay, we can perfectly classify the images. Okay, These are the basic building blocks of a convolution neural network. First, first we'll do the feature learning part, and then we'll do the classification part. Okay. Now, so we'll go in detail about each layer and each block. Okay. So feature learning. So we all know that in feature learning, we'll have convolution layers, rectified linear units, that means ReLUs, pooling layers like this. So all these are used for detection of edges, shades, lines, curves. Okay, so we will extract features. Features like edges, shades, lines, and curves. Okay, we will extract those features. Okay, so based on these features and by using fully connected neural network, okay, we will assign a probability for the object on the image, okay, being what the algorithm predicts it is. That means we can perfectly classify whether the image belongs to birds category or whether the image belongs to different dogs category or cat category like that. It is a small example. Okay. So first we will discuss about the feature learning part. So in feature learning, we'll have a convolution layer. Okay. Here, let us consider a 5 by 5 input image. Okay. So I have considered a binary 5 by 5 image. That means the pixel values are either zeros or ones. Okay, but if you consider a gray level image or gray scale image, then the pixel value ranges from 0 to 255. Okay, here I have considered a binary a binary image, which is of size 5 by 5. Okay. Now in convolution layer, so our input image, it will be multiplied with a filter. Okay. That means it will be multiplied to get that or to extract features like edges, curves, lines. Okay, normally these filters are also termed as kernels. So first the input image is multiplied with a kernel such that we'll get the features. Okay, we'll detect the features like edges, curves, lines. Okay. Now a kernel is here I have considered a 3 by 3 kernel, 3 by 3 filter. So if you multiply a 3 by 3 filter like this, okay, so if you multiply a 5 by 5 input image with a 3 by 3 kernel, the convolution output will be like this. Okay, first, so look at this. So look at this one and this one. First, one is multiplied with this one is multiplied with this one. So 1 into 1 plus. So this one is multiplied with 0. So 1 into 0 plus this one is multiplied with this one. That means 1 into 1. So 3 by 3 completed. Next, let us come here 0. So plus 0 is multiplied with 0 here. Okay. Next, 1 is multiplied with 1. So 1 into 1. Like this, multiplying and adding, you will get a sum of 4. So the first column, first row, first column is occupied. It is having a pixel value of 4. Next, we'll start from this one. Okay, we'll take this one. So 1 into 1, next 1 into 0, 0 into 1, 1 into 0, 1 into 1, 1 into 0, 0 into 1, 0 into 0, 1 into 1. You will get 3 as the output. So here, you'll have 3. Like this, after convolving, we'll have the feature like this: 434, 243, and 2, 3, 4. So this is the convolution output. Okay. Now, so here I have considered a 32 by 32 input image and a 5 by 5 kernel. So this is input image and this is kernel or our filter. So the output will be like this: 32 minus 5 plus 1. So you'll have 28 by 28. So the feature matrix, the feature map or the feature matrix will have the size of 32 minus 5 plus 1. Okay, you will have the size of feature matrix as 28 by 28. So this is the output of convolution operation. So we'll get the feature maps like this. Okay, now how we will identify edges or curves or shapes? Okay, here I have considered a curve like this. The curve is right bended. Okay, this is the curve. So as it is right bended, if you observe, okay, so if you observe, so we need to identify features which are right bended. The filter we'll apply is like this, such that we'll get a curve detection filter which is right bended. So let us take a rat image. Okay, so let us apply rat image to our filter kernel. The kernel is like this. So if you observe the multiplication and summation, okay, so 50 is multiplied with 30, then another 50 is multiplied with 30, multiplied with this 50 is multiplied with 30 like this. So we'll have a very large number, 6,600. Okay, so the multiplication and summation results in a large number. That means we are getting a very good response. We will get a very good response if the kernel, if the input contains the same kernel. Okay, so look at this. Basically, in the input image, if there is a shape that generally resembles the curve that this filter is representing, then all the multiplications and are summed together will result in a large value. So we are perfectly matching with the filter. Okay. So here I have considered a filter, which is a right-handed filter. Okay. But we are applying it to the input image, okay, in this area. So in this area, the pixels are distributed like this. So if you convolve this image with this right bended curve feature, okay, the multiplication and summation operation will result in 0. That means, okay, we are not having any right bended curves. Okay, here if you observe, it is a left bended curve. It is just like a half circuit. Okay. Here in the kernel, we are not having a kernel which will detect a right left bended curve. Here we have applied a kernel which will detect features like right bended. Okay. So like this here, I have just for example, I have applied a line detector which will detect lines. Okay, whether they may be right bended or they may be left bended or they are crossed lines or straight lines, all this. Like this, we can detect them. Okay, so like this, we have so many filters. Okay, if you observe, so here I have considered the feature map of AlexNet. We have a convolution neural network named as AlexNet. In AlexNet, so this one, this is used to detect crossed lines. So this filter is used to detect crossed lines. Okay, so like this, we have so many filters used to detect lines, curves, shapes, okay, and also colors. Now, so let us consider an edge detection filter. So this is the edge detection filter. If you apply this edge detection filter to this image, it will perfectly detect the edges like this. The output of uh, convolving this image with this edge detection kernel is this one. So you can observe that the edges are perfectly detected. Okay, so this is sharpened filter. So the image will be sharpened like this. Okay, like this we can have so many filters. This is a identity filter. That means if you convolve with identity filter, you will get the original image. Okay, convolving with the identity filter, we will get original. Okay, so here I have shown one type of edge detection kernel. Here you can observe different edge detection kernels. All these are edge detection kernels or edge detection filters. All these are edge detection. So we have already seen this sharpened filter. This is box blur. That means sum, total sum. You'll get 9 by 9. So it will be equals to 1. This is Gaussian blur, Gaussian noise. We are applying Gaussian noise. Okay. So by using convolution, okay, we can extract features like lines, okay, curves, shapes. Okay. Now, we'll observe padding, another operation in convolution neural networks. So if it is the original image, that means it is only a 4 by 4 image. Okay, we will pad it with 1. That means padding with 1 with 1 means we will add, okay, zeros, and then we will add a column, okay, and a row like this. Okay, and left side also we'll add another column and bottom another row with zeros, such that we can apply a 3 by 3 kernel like this. Okay, so we can multiply a 3 by 3 kernel like this and that. So first we'll multiply this with this one, and then we'll multiply and take the sum with this, and we'll multiply and take the sum, okay, with this one, okay, and then multiply, take the summation with this. So like this, and this padding will helps the image to get better features. Okay, padding helps the convolution operation to get the better features. Yeah. So we will go to after every convolution layer. So just if you go through any literature, after every convolution layer, we will have an operation known as a ReLU. Generally, all the convolution neural networks, almost 95% of convolution neural networks, you can find a ReLU after every convolution layer. So why we are using ReLU means just ReLU is an activation function. Okay, so why we are using this activation function means we all know that convolution operation is a linear operation. Just we are multiplying and then summing. So our operation is a linear operation. Okay. So if you use an activation function which makes the linear feature space into non-linear feature space, okay, then the network will converge very fastly. Okay, the network will converge very fastly. That means, so why we have to use activation function means fast conversing. Fast conversing. That means, so we are making the network fast conversing by making a linear thing into a non-linear one. Linear one into a non-linear one. So here, as convolution operation is linear operation, we are converting it into non-linear so that our network will converges very fastly. Okay, so here we have different types of activation functions. So we have sigmoid. Sigmoid means it is just like this. Okay, +1, -1, or tan H or ReLU. But ReLU, almost 95% will use a ReLU. Okay, so ReLU means, okay, we convert linear convolution operation into non-linear. So how we are making a linear one into non-linear one. Okay, so here in ReLU, in rectified linear unit, all the negative values, they are forced to be 0. So all the negative are 0. Okay, and positive, they will take the same positive. So the function will be like this. Okay, so we are introducing non-linearity. Okay, we are introducing non-linearity. All negatives 0, all positives like this. So our function is like this. Okay, so this is about ReLU. So what? So in concise, ReLU is used to convert a linear one into non-linear. What is the advantage that you will get? Fast conversing. So if you apply ReLU to an image like this, okay, we will get an image like this. So all negatives are forced to be 0. We have only non-negative or positive values. So after every convolution layer, and ReLU, okay, we have a pooling layer. Okay, this pooling layer, it is used to reduce the dimensionality. It is used to reduce dimensionality. So why? That means If you reduce the dimensionality, then the training time will be very less. We require less computational power. Okay, so we'll reduce the dimensionality by keeping the important information. So how we can reduce the dimensionality? Using downsampling. Okay, using downsampling, we can reduce the dimensionality, and we have different types of poolings. Okay, we have max pooling, average pooling, sum pooling. Okay, so if you consider max pooling, that means, so here we have, if you apply a 2 by 2 1, then 1 4 2 6. So out of these 4 elements, pixels, so 6 is the maximum one. So the first element is 6. Okay, so in the second one, in the second 2 by 2, 2 7 8 5, the maximum one is 8. So that means we are keeping the important information, even though we are reducing the dimensionality. Here the maximum one is 4, and here the maximum one is 7. So we are reducing this feature map into this one. So here we have applied max pooling. Okay, not only max pooling, we will also apply average pooling. So what is the meaning of average pooling? So it is just nothing but average pooling means, if you take this first one, 1 plus 4 plus 2 plus 6, that means by 4, that means 13 by 4. The first element will be replaced with 13 by 4. Okay, like that we have max pooling, average pooling, sum pooling. We can also replace it with sum pooling. So the main aim of pooling layer is to reduce the dimensionality by using downsampling. Even though we are reducing the dimensionality, we are keeping, the important thing is that we are keeping the important information. Okay. So this is about pooling. So these are the basic building blocks of feature extraction. So if you observe here, first we have a combination of convolution ReLU, another convolution ReLU. That means after 2 layers of convolution ReLU, you can find a pooling. And our own NIDI, we can also use a ReLU here. And after convolution ReLU, we are using a pooling layer. So we are reducing the dimensionality. Okay. So if you reduce the dimensionality, the advantage is that the final, so after feature extraction, this is feature extraction. After feature extraction, we have to apply this one to a fully connected neural network. So for this fully connected neural network, as we are applying a reduced size output, it takes less computational power and less time to produce accurate outputs. Okay? Less computation. So this is how we are extracting the features. Okay, so after feature learning, that means after extracting the features and learning about the features, we are classifying the image. Okay, we are classifying the image, whether that particular image comes under cars. Here, if you consider this cars category or truck category or van category or bicycle category, that means convolution neural networks. Okay, they learn from the features. Okay, so first we'll apply some input images. From those input images, our convolution ReLU pooling, they will extract the important features. Okay, like edges, curves, shapes. Okay, okay, using filters. Okay, so our network will learn from those features, and After classification, we can perfectly classify whether that particular input image comes under which block. That means it comes under cars category or truck category or van category or bicycle category. Okay, so here fully connected means it is just nothing but a fully connected neural network, normal neural network. Okay. Next, the another important thing is that after fully connected neural network, we have a softmax of activation function. Okay, softmax activation. So the main important thing about softmax activation is that it takes a vector of arbitrary real valued scores, okay, and squashes it to a vector of values between 0 and 1. That means using softmax layer, as it is the last one, okay, it perfectly classify whether our input image comes under which category. Either 0 or 1 means in one category or the other category. Okay. Now, this is about convolution neural networks. So any doubts about convolution neural networks? And this is simple introduction about convolution neural networks. Now we will go to Singara. Singji. Any doubts? Okay. Now we will discuss about the self-driving cars, and in self-driving cars, how we can apply our deep neural networks or convolution neural networks. Okay. So basically, before applying CNNs, we have to understand something about self-driving cars. Okay, the sensors in self-driving cars. Okay, now in self-driving cars, we have mainly four main parts. First one is perception, localization. 1 minute. We have perception, localization, prediction, and decision making. Okay. Now, so if we discuss about the perception, one of the most important properties that self-driving cars must have is perception. Okay. It helps the car to see the world around itself. Okay. It recognizes, classifies the things it sees. Okay. Perception helps to recognize and classify the things that the self-driving car sees. In order to make good decisions, okay, our self-driving car or autonomous car, they have to recognize the objects instantly, so that the car needs to see and classify different objects. Like when it is going, we can have traffic lights. Okay, we have to classify traffic lights, pedestrians, road signs, walkways, parking spots, lanes, etc. Not only that, okay, it also needs to know the exact distance between itself and the objects around it. Okay, so perception is more than just seeing and classifying. It enables the system to evaluate the distance and decide to either slow down or brake or to accelerate. Okay, to achieve such a high level of perception, an autonomous vehicle must have three sensors. First one is camera, lidar, and radar. So first, we'll discuss about camera. The camera provides vision to our autonomous vehicle. Okay, we can do multiple tasks like we have discussed earlier: classification, segmentation, and localization using convolution neural networks. Okay, so in order to perfectly identify traffic lights, pedestrians, road signs, walkways, we need the cameras need to have high resolution and represent environment accurately. Okay, the environment around itself, it must represent perfectly. In order to make sure that the car receives visual information from the every side, we may have cameras front side, back side, left, and right. So if you observe a Tesla autonomous vehicle, we have 8 different cameras in 360 degrees view to have a 360-degree view. Okay, in NVIDIA self-driving car, we have front, back, left, and right. Okay, only in some self-driving cars, we have 3 cameras, NVIDIA. In some self-driving cars, we have 4 cameras from NVIDIA. Okay, so no doubt we have 3 to 8 cameras to have 360-degree view. And also these cameras must provide a wide range of view. So we all know that at present we have cameras can produce high resolution images up to 200 meters. That means we have only a short range view. Okay. Another problem and another challenge is uh, when we are parking, the camera also provides, it should provide the panoramic view for better decision making. So the cameras do all the perception related tasks. Okay, but the main problem or challenge with the cameras is during the extreme condition where the cameras will fail. The extreme conditions are like this. Okay, they may not capture some noise and discrepancies. Okay, during extreme conditions like fog, heavy rain, or during the night time, we may not get accurate data from cameras. Okay, so to overcome these limitations, we need sensors that can work without light and assure the perfect distance and measure, not only assuring, it has to measure the distance. So for that purpose, we will use a sensor known as LiDAR. LiDAR stands for light detection and range. So using LiDAR, we can measure the distance of objects. So how we can measure means we will fire a laser beam. Okay. Then we'll measure how long it takes for it to be reflected by something. Okay, by doing this, we'll measure the distance of objects. Okay, so if you compare it with the camera, a camera can only provide the car with images of what's going around itself. That means we can have only 360 degrees view. Okay, but if we combine the information from camera with LiDAR sensor, okay, we will get the depth of the images. That means we can have the 3D perception. Okay, the 3D perception of what's going around the car. That means the lidar perceives spatial information. But in 2019, if you go through Google, you can find this statement. Elon Musk openly stated that anyone relying on lidars are doomed. Why? Anyone relying on lidars are doomed. So just now, I told you that if you combine the information coming from camera along with lidar, we'll gain depth in the image. Okay, it means we'll get the 3D perception. But the problem is that lidars are also having some limitations. So in the time, the lidar, when it fires lasers or send light to measure the distance of the nearby object, okay, no doubt it works well during night or dark environments, but it won't work well during rain or fog. That is the problem. During rain or fog environments, okay, we cannot able to measure the depth. We will not get the 3D perception. That is why, along with camera and lidar, we also need radar. Okay, we also need radar. So radio detection and ranging. So up to now, we all know that radar is a key component in many military and consumer applications. Okay. So radar will calculate the distance using radio wave signal. So as they are using radio waves instead of lasers, they will work in any conditions, even if you have heavy rain or fog. Okay, as they are using radio waves, they can perfectly get the information. They can perfectly get the 3D depth. Okay, we can perfectly have the 3D perception. So if you observe here, so this image, so this is the LiDAR image. This green one is the car. So it measures the distance between the nearby objects and the car by firing the lasers. Okay. Here, if you observe here, when compared with this one, if you look at this, okay. So here we are getting more information. And if you consider radar. So if you combine the information from camera, LiDAR and radar, okay, we can perfectly assess the 360 degrees view, 3D perception and depth. Okay. And another thing is that when we are using radar data, it should be clean. Okay, here you can observe so much of noise. Okay, so this image should be cleaned. So in order to clean, if you clean that image, we can the system, the convolution neural network can take a good decision, good prediction. So for that, we need to separate weak signals from strong. So separating weak signals from strong signals means it is just nothing but thresholding. Okay, using thresholding, we can some noise. And also we can use a fast Fourier transform to filter and interpret the signal. Okay, so this is about camera, LiDAR and radar. Next one is localization. Okay, so localization algorithm, it is used to calculate the position and orientation of the autonomous vehicle. Okay, it is used to find the position and orientation. So normally it is known as visual odometry. In order to map this visual odometry, we will use a mapping algorithm known as, and normally this HydraNet proposed by Tesla, they are using simultaneous localization and mapping. Simultaneous SLAM algorithm. They are using algorithm SLAM. Okay, to come SLAM, it is used to find the position and orientation of the vehicle, autonomous vehicle. Okay, so here deep learning finds a very good application. Deep learning, it is used to improve the performance of a visual odometry. Not only it improves the performance, it will also classify the objects. Okay, so here uh, Tesla or Google or NVIDIA, they are using convolution neural networks like POSNet, okay, BlockNet, BlockNet, BlockNet plus plus. Okay, these are the some of the frameworks used by different companies. Okay, used to estimate the 3D position and also orientation. Okay, so localization is very important. After localization, okay, along with localization, we must have, we also need prediction. We also need prediction. Okay, why prediction is important means the basic problem is like this. Understanding human drivers is a very complex task. Okay, even though the car has 360-degree view of its environment, okay, once the total environment is fed to deep learning algorithm, okay, for different situations, we can come up with different possible moves that other road users might make. Okay, the sensors in self-driving cars, okay, enable them to perform tasks like image classification using convolution neural network from the data coming from camera, lidar, radar. Okay, okay, we can classify the images, we can detect the objects, we can segment the objects, and we can localize. Okay, so using deep learning, we can interpret complex vision tasks, localize the environment, enhance the perception, and actuate the kinematic maneuvers in self-driving cars so that the safety will be ensured. So if you take the decision-making part, okay, if you take the decision-making part, so autonomous vehicles need a system. That means we need to develop an algorithm, convolution neural network, in such a way that the system must be dynamic and precise in an uncertain environment. Okay, if you look at the image, here we have an autonomous car. It is moving towards an intersection. So it is moving, this car is moving towards an intersection. So in this scenario, the self-driving car has to predict whether the other car will go straight, left, or right. In each case, the car has to decide what maneuver it should perform to prevent the collision. In order to make the decision, the car should have enough information so that it can select necessary set of actions. Okay, our sensors will help the car to collect the information, and the deep learning algorithms are used to give localization and prediction. Okay, in general, the decision making in self-driving cars is a hierarchical process. The four main components of this decision making is, first we need to plan the route. We need to plan the path. Okay, planning a route and planning a route means first we have to enter into the environment. Our autonomous vehicle, it should enter into the environment. The car should plan in such a way that we need to have a best possible route from its current position to the required destination. Okay, we need to find optimal solution among all other solutions. Okay, we for this we can take the example of Google Maps. So if you observe Google Maps, okay, the Google map will give the longest route with minimum traffic, okay, route that takes more time, route that takes minimum time, like. So based on, we can also use that information for path planning or route planning. The second component is behavior arbitration. So once we plan the route using the information, okay, we need to navigate, and the car need to navigate itself through the route. Okay, the car knows about the static elements like roads, traffic lights, intersections, road congestion, average road congestion. Okay, but the autonomous vehicle, it doesn't know exactly what the other road users are going to be doing throughout the journey. Okay, this uncertainty in the behavior of other road users will be solved by a method known as a probabilistic planning algorithm. Okay, the Tesla, it is using MDP, Markov DP. Okay, so next one is motion planning. Once the behavior layer decides how to navigate through a certain route, the motion planning system, okay, it orchestrates the motion of the car. Okay, so it must be feasible, comfortable for the passenger. Okay, along with this, we need to decide, we need to include speed of the vehicle. Sometimes we have to change the line. Okay, different situations which should be relevant for that particular environment where the car is in. Okay, another important component is motion planning. Okay, so motion planning, okay, sorry, vehicle control. So this vehicle control, it is used to execute the reference path from the motion planning system. Okay, so not only from the information coming from camera, lidar, radar, we need to have a perfect, precise localization. After precise localization, we need to take a perfect decision. So for all these things, we are using deep learning algorithms, different convolution neural networks. Okay, so if you our localization, it enables the car to know its initial position, orientation. Prediction, it creates a number of possible routes, possible actions. Okay, based on the environment around the car. Okay, an environment where we need to go, the destination. But the main question here is which option is best out of the many predicted actions. For this, Tesla is using deep reinforcement learning, a convolution neural network algorithm known as deep reinforcement learning. In this deep reinforcement learning, okay, for behavior arbitration, okay, DRL, in the DRL, we are using a Markov decision process. In this Markov decision process also, the route will be optimized using Bayesian optimization. Okay, the route will be optimized using Bayesian optimization. Okay, so in order to tackle the problem of finding the best move for the car itself, okay, we need to model a deep learning model, more deep learning system, which is optimized with Bayesian optimization. It is the best optimization, I think. Okay, so based on this information coming from sensors which are applied to convolution neural networks, we can perfectly make a decision. So now we'll discuss about different convolution neural networks used by Tesla and NVIDIA. So basically at present we have three convolution neural networks by three different companies: HydraNet by Tesla, ShuffleNet by Google Waymo, and NVIDIA self-driving car. But in this session, we will concentrate mainly on HydraNet and NVIDIA self-driving car. Here, if you observe HydraNet, we have different branches. Okay, we have different branches, and the information from these different branches, okay, will be controlled by gate. Okay, so this HydraNet, it is a dynamic architecture. In this dynamic architecture, we have different branch. That means we have different CNN network which are assigned different tasks. Okay, these branches, and normally these blocks or networks, normally they are called here in HydraNet as branches. Okay, so the basic idea of HydraNet is to get various inputs and feed them into a task-specific convolution neural network. So if you take the context of an autonomous car, once the input data set and then we have different input data set. That means one input data set may be of a static environment like trees, roads, lines, road railing, like that. Another input data set can be on roads, different roads. Another one is on traffic lights. Okay, like this. So these inputs are trained in different branches. Okay, each branch will train different input, will be trained with different inputs. Okay, input data sets. Okay, during the inference time, during the inference time, this gate, the green one, the gate will choose which branches to run. And the combiner, blue one, the combiner aggregates the branch outputs and makes a final decision. Okay. So if you observe a Tesla car, you can find 8 cameras. So we are getting the information from 8 cameras. Those the input data will be divided. Okay. So one input data set. Okay, we'll train with different input data sets. Okay, during testing, that data will be applied to our testing algorithm such that it can perfectly classify whether it belongs to road or road railing, or whether the image is a tree Okay, traffic light like that. Okay, now normally to get a perfect weather here you can observe when we are going through an autonomous vehicle of a Tesla, the car will access the images like this. It will segment the images like this. So bounding box, they will do, okay, bounding box segmentation normally. Okay, for bounding box segmentation, we can, Tesla is using units. Okay, okay, we can also use YOLO 3 or YOLO 5 segmentation algorithm says that we can perfectly get the information, the environment around our autonomous vehicles. Okay. Another important feature of Tesla HydraNet is it projects a bird eye. That means it can create, if you look at the image, the figure, okay, it can create a 3D view of the environment from any angle. Okay, that means we are giving the car much more dimensionality to navigate. Okay, so our algorithms will be perfectly, they can work perfectly. Okay, and another important thing is that here in Tesla, they are not using LiDAR sensors. They will only use cameras and radars. They have only two sensors, cameras and radars. Although LiDAR creates a depth perception for the car, okay, uh, the convolution neural network, HydronNet, is so efficient that it can stitch all the visual information from the 8 cameras in it and create a perfect depth interception, depth perception. Okay, so now we'll discuss about NVIDIA self-driving car, NVIDIA autonomous car. If you look at the block diagram, you can observe that we have three cameras, okay, one steering angle. So based on that, okay, the information coming from the cameras, okay, and along with radar and LiDAR, okay, we will train all the data coming from the cameras, LiDAR, and radar. Our network will predict in such a way that our network will control the steering angle. Okay, so for error adjustment or for that to correct the adjustments, to correct the weights of the network, okay, we are using a back propagation algorithm in NVIDIA self-driving cars or autonomous cars. So this is about NVIDIA autonomous car. Okay. So like this, we have, so we can use convolution neural networks, deep learning to train the data coming from cameras, LiDARs, radars, and we can perfectly get the precise location of the car, orientation of the car. We can get perfect environment around the car, 360 degrees view along with 3D perception. Okay, by training the network with deep learning. Okay, we can get a perfect prediction, perfect decision making with deep learning. So this is about deep learning for autonomous vehicles or self-driving vehicles. And basically, if it is an autonomous car, it is an electric vehicle. Okay, thank you. Thank you, Bhakti Singh sir, for giving me this opportunity. Thank you very much. Any doubts?
అయిపోయింది కదా వచ్చింది రెడీ.
If you have any discussions to discuss with the speaker, please ask, sir.
ప్రస్తుతం ఖాళీగా ఉంది.
Thank you very much, sir, for your valuable session on behalf of Department of EEE and VVIT. Thank you. Let us end the session. Tomorrow, the last session will be at 9:30 a.m. Thank you.